Okay, so let's look at a couple. It is just going to be a couple of fairly simple questions involving simple harmonic motion. Most of the IB questions involving this topic actually, the short answer ones at least, actually involve a combination of the equations that you've looked at so far, plus also some energy terms. So the energy part isn't that difficult, well, ish. And I think we'll have a deeper dive into at least one big example question after that. So, multiple choice question. The period of a particle undergoing simple harmonic motion is t. The ratio acceleration of a particle over displacement of a particle from its equilibrium position is proportional to one of those options. Best approach here. What do we know? What equations do we know? What's it talking about? So the ratio of acceleration of a particle. Well, what's the equation for the acceleration of a particle undergoing SHM? It's a equals minus omega squared x. Displacement of a particle from its equilibrium position, that's just x. So a equals negative omega squared x divided by x. Negative omega squared x divided by x is giving you negative omega squared. But that's not one of the options there. Instead you've got omega equals 2 pi over t. So if it's omega squared, then t is going to be omega over 2 pi. So t to the power minus 2 is the correct answer. Question 21 from the 2016 paper says that a mass is connected to a spring on a frictionless horizontal surface as shown. So this is a common SHM example. The spring is extended beyond its equilibrium length and the mass executes simple harmonic motion. In other words, when it's let go, it will oscillate backwards and forwards. Which of the following is independent of the initial displacement of the spring? So in other words, what doesn't depend on the initial displacement of the spring? Well, it can't be B because B is the total energy. If you extend it more, then the spring energy is going to go up. So it's going to be bigger. So the total energy is going to be bigger. Until you let it go, it's not going to have any kinetic energy. I mean, we'll look at the energy a little bit more detail soon. But if you just think about it, you're stretching it, it's got more spring energy. So that's going to be very dependent on the initial displacement of the spring. And the maximum kinetic energy of a mass is also going to be dependent on that, because as it passes the equilibrium position, all of that potential energy will disappear and it'll just be kinetic energy. If the initial potential energy was dependent and therefore the total energy was dependent on the displacement, then the kinetic energy must also be dependent on the displacement, because it's the same thing. And if the kinetic energy depends, then the speed will as well, the average speed of a mass. So that kind of only leaves the angular frequency oscillation as the right answer. And if you look at the equation, a equals negative omega squared x, omega is the angular frequency. So what this equation is telling you is that the acceleration is proportional to the displacement, x. What it doesn't depend on is the constant of proportionality, which is negative omega squared. So the angular frequency does not depend on the initial displacement of the spring, and the correct answer is A. Thank you very much.